So this is problem 7 out of chapter 7, and what we have is a little angle that's 4 inches by 3/4 and 4 inches by 3/4. I'm going to break it down into two pieces. This would be piece 1, this will be piece 2, and we're going to go ahead and do the centroid on this first before we get into moment of inertia, just to kind of run through that with you. But you will notice, should notice that this is going to have symmetry once we get done with it. And we're going to use this point as our point of origin to work from for our centroid values. And we're going to call this the x direction and the y direction. So we'll call the shape, we'll have shape 1, shape 2. So we're going to call this shape 1 and this shape 2. So we're going to have a shape area x, ax, y, and ay. Okay, so shape 1, we're going to have an area of, this side is going to be 4 minus 3/4, so 3 1/4 times 0.75 gives us an area of 2.4375. So x is the distance from here to the y bar of that, so it would be half of 3/4. A times x is going to give us 0.9141. So for this, we would have this side is 3 1/4, half of that plus 3/4. And what you're going to wind up with is 2.375. So we're going to take this times that, gets us 5.7891. Okay, so for shape 2 is going to be an area of 4 times 3/4, gets us 3. And x is going to just be half of 4, so that gets us 2. 2 times 3, 6. This is going to be, for y, half of 3/4, so that gets us also a 0.375 times my area, 1.125. So we're going to have 5.4375, and the sum of the axes, 6.9141, and the sum of the ay's, 6.9141. So we have x bar and y bar. The sum of the axes divided by sum of the area, gets me 1.272 inches. Looks like I crowded this. Let me delete this. We'll drop that down. But you can see that we're going to also have 6.9141 divided by my 54375 gives me 1.272. Okay, so what that's giving us then is it's telling us that we're going to have our x bar, or our y-axis out here, our x-axis here, and that's what we're going to be utilizing for getting into the moment of inertia. So let me go ahead, we're going to put that on there, and then we'll drop into the moment of inertia. Okay, so we've taken and we've added the X bar and Y bar. So this is your X bar distance to the YY centroidal axis, and this is your Y bar to the XX centroidal axis. Same as dealing with shape 1 and 2. Since this has symmetry, you're going to see something very interesting happening here. And notice actually where the centroid is in this case, it's actually out here. And it's not even on the part, which can happen. Okay, so we're gonna run the parallel axis theorem on this. We're going to do shape. We're going to do the x's first. So we're going to do I, x, c, and then we're going to have area for that shape, the d distance, scoot that over a little bit, the d distance, ad squared, and then ultimately our I, x value. So for shape 1, so we're going to have, this is shape 1. So it's 0.75. This is your base times the height cubed, which is 3 1/4. So 3 1/4 cubed times 0.75 divided by 12. And when you run that, I believe you should get 2.1455. Now you can round those. I usually round everything at the end. So what we have now is 0.75 times 3 1/4. So the same area that we had calculated before, 2.4375. So the d distance, remember, you're going from x centroidal axis to x centroidal axis. So this axis as compared to the axis of this guy. So this axis would actually be 1/4 up plus half of 3 1/4 minus the 1.272, and that would be the distance of separation. So again, 0.75 plus half of this side, which is 3 1/4. So half of 3 1/4 plus 0.75, and that total minus this. And what we'll find out is we get for that D, when I did my math, you can check this, I got 1.103. So again, it's the x of this guy to the xx of this guy. So we're looking at that distance. So we're going to square that, multiply it by that. And it's real easy to forget to square that, so make sure you square it. 2.966. So we're going to add those two together. We're going to come up with 5.112. So I'm going to start to round. Okay, so we're ready for shape 2 now. Shape 2. So this is your base, this is your height. So 1/12 the base times the height cubed. So the base is 4, the height is 0.075, and 1/12 of that. So this isn't going to give you much stiffness in this direction. So what this is saying, when we're loading it either this way or this way, this guy's doing most of the stiffness. This is not giving you much. Area would have been the 4 times 3/4. That's the same area we had before, so that is 3. So now we're looking at this guy's x-axis as compared to this guy. So the distance from x-axis to x-axis here. So this is half of 0.75. So you're looking at that minus that. So half of 0.75 minus that gives me a d distance of 0.897. So we're going to square that, multiply it by the 3, and we get 2.414, to which we will add this to that, and that gets us 2.554. We're going to sum that, and we get 7.666, or you could probably call it 7.67 inches to the 4th. So this is our I, X, X. Okay, so again, we're looking at this way, loading it here or here. Okay, so now we're going to look at it coming in this direction. So that's, we're going to basically rotate it 90, if you will. IYC area D, which is going to be going in this direction, A D squared I Y. So shape 1, now we're looking at shape 1. This is now the base, 3 1/4 times the height. So that's going to be 3 1/4 times 0.75 cubed divided by 12. And what that gives us, that's a really small amount of stiffness. That's 0.1143. So that's not contributing much. The area of that is the same area as we just calculated. So that's 2.4375. Okay, so we're looking at the distance going from this guy's centroidal axis, okay, which would be 1/2 of 3/4 over, and this. So this 1.272 minus 1/2 of 3/4, and that's going to give us 0.897. So we're going to square that, multiply by that, and we get 1.961. Okay, so we take and add these two together, and that gives us a grand total here of 2.076. Okay, so now we're looking at shape 2. So shape 2, this is shape 2. This is your base. Now this is your height. So it's 1/12 the base, which is 0.75, times the height cubed. So that's 4 cubed times 0.75 and 1/12 of that. And that gives us a moment of inertia of 4. Area is the same thing as we had before. It's 3. Okay, we're comparing this guy's x-axis, or y-y rather, which is here, that would be 2. So 2 over minus that difference is the axis to the axis comparison. And that gives us 0.728. We're going to square that, multiply it by 3, 1.59, and add that to 4. So that gives me 5.590. Sum this, and interestingly, what you'll notice is you get the exact same number. A lot of this has to do with the symmetry. This is what you call an equal leg angle, because they're the same distance this way. And so notice the x-bar and the y-bar distance are the same, and the moment of inertia are exactly the same. So loading it this way or loading it this way would have the same rigidity or the same stiffness. So this is an interesting one because of that, and that's why I also wanted to do the centroidal axes for you, to just make sure that we're okay with that.